Hello, today we're going over section, or actually chapter 10.8, the probability of compound events. Now what a compound event is it's two things at once. So like the probability that you flip heads on a coin and roll a 3 on a die. So it's two different situations that are happening that each have multiple different outcomes. So we could flip heads or tails, and we could roll a 1, 2, 3, 4, 5, or 6. So two different events, compound, just like compound words. Like your compound words, do not, don't. You're putting them together. What a tree diagram is it's something that helps you to interpret your compound events. So a tree diagram, it branches off. So we'll start off with rolling the die. Like you have, and we just have a 3-sided die in this world, which doesn't exist. But it's the probability of getting a 1, 2, or 3. And then we also have heads or tails. So we could roll a 1 and get heads, or 1 and get tails. 2 head, 2 tails, 3 head, 3 tails. So our total number of outcomes is 1, 2, 3, 4, 5, 6. So your tree diagram is branching off like that. You could also have 3 events, so 2 plus things, 2 or more things happening at once. So here's an example for you. It says a pet store sells aquariums in 3 shapes: hexagon, pentagon, and rectangle. And there's 2 different sizes, 10 gallons and 20 gallons. So you want to know how many different fish tanks can be made from the different shapes and sizes. So there's 2 ways that you could do to figure that out. You could use a table like they did here, or this here is a tree diagram that looks a little nicer than the one that I made on the other page. So here in their table, they did hexagon for 10, pentagon for 10, rectangle for 10, and then hexagon for 20, pentagon for 20, and rectangle for 20. So they made sure that they got all the different options in there. The tree diagram does a very similar thing. You have your hexagon, your pentagon, and your rectangle as your shapes. There's also 2 different sizes of each thing. So each shape needs to have 2 branches coming off to represent the sizes. And then over here in the sample space, they wrote it a little better so you could see a hexagon at 10, hexagon at 20, pentagon at 10, pentagon at 20, and so on. So your sample space is your total number of outcomes. And in this case, that would be 6. Another way that you can figure that out is by taking the number of outcomes you have for shape times the 2 different sizes, right? So we're timesing by 2 because that's how many sizes there are. And we get our total number of outcomes of 6. And we'll go into that a little deeper. So here, Miranda has 5 shirts and 4 pairs of pants that she uses for her work clothes. How many different outfits can be assembled using 5 shirts and 4 pairs of pants? So outcome, or actually I'm going to label it this. So she has shirts and she has pants. She has 5 shirts and 4 pants. What you do to figure out the total number of outfits that she can assemble is you multiply those together and get 20. So her total number of outfits that she could have is 20. We also have students being assigned a temporary password for the first time they visit the computer lab. The temporary passwords consist of a letter, number, letter. We want to know how many temporary passwords are out there. So it wants us to make a possible list of the outcomes. And we're going to skip that because that's too much work. So all you do is you go, okay, so our letter options here, there's 3 different options for letters. There are 2 different options for numbers, and then 3 different letter options again. All you do is multiply those together. 3 times 2 is 6. 6 times 3 is, brain fart, 18. And so the total number of temporary passwords are 18. Once again, we're just going to keep going over examples for you. Pizza Shop has regular, deep dish, and thin crust pizzas. 2 different cheeses and 5 toppings. So how many 1 cheese, 1 topping pizzas can be ordered? So we know that there's cheese, toppings.
Where is Sarah?
Do you want to say hi to the class?
Oh,
I'm
hi.
doing a video right now. I'm going to keep it going. Cheese, toppings, and crusts. The amount of cheese is there's 2 different cheeses. There are 5 different toppings, and then regular, deep dish, and thin crust. So 3 different crusts. You multiply those together, and 2 times 5 is 10, 10 times 3 is 30, so there's 30 different pizza combination options. So here, when you know the number of outcomes, you can find the probability that a compound event will occur. So now the number of outcomes is, Mrs. Smith says bye. So the number of outcomes will be in the denominator. The number of that, of what like you want, so number of the favorable is your part. So part over whole. Can't say that anymore. So here Emily has had 2 counters. Each counter had one side marked with an E and the other side marked with a J for Jacob. So you've got E and J. Both counters are tossed. If one lands with E up and the other lands with J up, Emily wins. Otherwise, Jacob wins. So what is the probability that Emily will win? So our coins could land either EJ, EE, JJ, or JE. So there's a total of 4 outcomes. If one counter lands with E up and the other with J up, Emily wins. So that happens 1, 2 times. So the probability that Emily will win is 2 out of 4, or 1/2, or 50%, or whatever else you want to say. So there's a 50-50 shot that Emily will win or Jacob will win. Our next problem wants us to know what the probability of choosing a 5-letter password that consists of only vowels, if each vowel can be used more than once. So we have a 5-letter password. So 1, 2, 3, 4, 5. We can only use vowels, so A, E, I, O, and U. There are 5 different vowels. So there's 5 different letters that could go here, 5 different letters that could go here, and so on for every single space. What we're going to do is we're going to multiply every single one together. So 5 times 5 times 5 times 5 times 5. And we end up with 3,125 total possible outcomes. We want to know the probability of just choosing one would be. So 1 password out of 3,125. So your probability of randomly guessing someone's right is 1 3,125. So not very likely for you. The fundamental counting principle says that if an event M can occur in M ways and is followed by an event N that can occur in N ways, then the event M followed by the event N can occur in M times N ways. So that's just what I was saying earlier, like if we're flipping a coin and rolling a die. The probability of a coin is 2, because there's 2 different outcomes, times the total number of outcomes on the die, which is 6. So your total amount of outcomes is 12. And that's just what we've been going over earlier, but the big fancy word for you here is the fundamental counting principle. And then finally we have the example, 3 number cubes are rolled. What is the probability of rolling 3 5s? So this one we have our cube 1, cube 2, cube 3. We know the probability of rolling a 1 5 is 1/6. because there's 6 different numbers, 5 is just one. So you have a probability of 1/6 for each and every die. You multiply that together. When you multiply fractions, you just multiply straight across. So 1 goes on the top, and 6 times 6 times 6 is 216. So the probability of rolling 3 5s is 1/216. So it's not likely that that will happen, if you remember going over those words the other day. So now I'm going to send you off onto your assignment. Good luck.